Everybody. The first speaker today is Stoll from Universität Bayreuth, and he will speak on minimization and reduction of plane curves.
Yeah, thank you very much. Can you hear me? Okay. Yeah, thanks to the organizers for organizing this workshop and the whole trimester, and for giving me the opportunity to talk. And thanks to you for being here for the first talk in a very long day of mathematics. I think we have 5 talks today, right? Okay, so what I'm going to talk about is joint work with Stephan Elsen, who's now in Würzburg. And well, part of this is something he did some 15 years ago, and then there are some things I did some 10 years ago or so. And then recently we decided we should put this together and turn this into a paper, and then we actually did something new also, and that's what I want to tell you. So this will be a fairly explicit talk. So there will be an explicit problem, computational problem, which I'm trying to solve. So what's the problem? So for now, K is any field, but later it will be Q. So we can consider homogeneous polynomials of a certain degree in a certain number of variables over K. So such a polynomial, if it's not a zero polynomial, defines a hypersurface in projective space. And well, usually we are not interested in the specific equation, but in the hypersurface it defines. So we are only interested in this up to coordinate transformations on projective space. And of course, also, if we scale the polynomial by something non-zero, it doesn't change the hypersurface. So we can act on this by invertible matrices in n+1. Well, so n+1 times n+1 matrices, GN+1 over K, which acts on the variables. And then we can also scale the polynomial to get an action of the multiplicative group of K, and then we can combine the two and get an action of this product like this. So I want the matrix to act on the left, which means that I have to act on the right on the variables. But conventions differ a little bit. So later when we talk about implementation magma does it the other way around. So the matrix you have to use there as a transpose. Okay, and then, well, if we do this over Q, we can obviously scale the polynomial so that it has integral coefficients, maybe coprime integral coefficients. So we can look at integral polynomials. But then, of course, we can still do coordinate transformations over the rationals. And this may actually give us something that has smaller integral coefficients. So the problem is, given such a homogeneous polynomial of some degree d in these n+1 variables with integral coefficients, find another representative of its orbit under the group over Q that also has integral coefficients, and so that the coefficients are small in some sense. So why would one want to do this? So I mean, of course, one thing is equations with small coefficients are just nice to have for aesthetic reasons, but also for practical reasons. If you actually want to do computations with your hypersurface, so later it will be a curve in P2, then it's definitely good to have an equation that has small coefficients, because then the computations you want to do will involve small numbers and not large numbers, and that makes them usually much easier. So for example, if you want to search for rational points on your hypersurface, then usually they are easier to find if you have a model with small coefficients. That's sort of the connection to rational points here of this talk. Okay, and just to demonstrate a little bit what I mean. So suppose you have done some computation, some interesting curve that has a, say, plane model of degree 5 for some reason, and you get this equation. But I mean, you have good reasons to believe that actually this should be, I mean, say, it has some kind of modular interpretation or so, and you know the level is small or so, so we are convinced that there should be a much simpler model of this. And so what you want to have is some computer program that you can give this equation to, and then you wanted to tell you, well, you should perhaps consider this matrix, apply it to the polynomial, and then you can divide it by this number, and then what you get is much simpler than before. Yeah, so that's the idea. And before anybody asks, of course, the example was done the other way around, but so I took this and I hit it with a random matrix with, well, 2-digit coefficients, and then, I mean, that's something, I mean, typically what you get looks like this. And then to get back, I mean, you have to take the aggregate matrix, which has 4-digit coefficients roughly. Okay, any questions so far? Good. Now this problem can be split into 2 parts. So according to the title of this talk, so the first is minimization. So this refers to the fact that you sort of want to have a model that has sort of best possible reduction properties, modulo primes. One way to formulate this is to say you want the invariance of your homogeneous polynomial to be small in absolute value. I mean, there will be some integers. And this means that you have to remove prime powers from these invariants as far as possible. So in the best case, you remove them completely, more or less, and then roughly it means that you get something of good reduction. I mean, I should mention that, of course, we are sticking to this projective model we have up to automorphisms of Pn. So of course you can have cases, say you can have plane quartics that have good reduction at some prime, but where the reduction is not a plane quartic but a hyperelliptic curve, and then of course your plane quartic model will not have good reduction. But you can still get the kind of best possible reduction for the plane quartic model in this situation, which I think would be a double conic, something like this. Okay, then when we have done this, so we have removed prime powers from the invariants as far as possible, what we get, we will call a minimal model, minimal representative of the orbit. So it has small invariants, best possible reduction properties in some sense, but it doesn't mean that it has small coefficients. I mean, if you take if you think of binary forms, or say of univariate polynomials as dehomogenized binary forms, if you shift the variable by a large number, then you get large coefficients, but you don't change the invariance. So small invariants don't mean that you get small coefficients. And, well, maybe before I go to the next subproblem, I mention here that to have a meaning for the statement that we want to remove primes from the invariants, I mean, you have to know how many powers or what power of a prime is contained in an invariant. So you need at least one invariant to be non-zero. So you can have bad polynomials such that all the invariants vanish, and then you have a problem, but they're usually not the ones that show up in practice. Okay, so if we have a minimal representative, which may still have large coefficients, we want to turn this into one that's still minimal but has small coefficients. This is the reduction part. And so to do this, we want to act on a polynomial by a unimodular transformation. So matrix that's invertible over the integers. So this does not change the invariance, at least not up to sign. If I could write SL and then would just leave the invariants as they are. But can still change the size of the coefficients, obviously, and we want to find one such transformation that so that the resulting polynomial has small coefficients in some sense. And so what I will focus on in this talk is the minimization part, in the case of ternary forms, so plane curves. I have one slide on reduction in this context, but I won't say much about it. The main reason being that the minimization part is the new one. Okay. Now, regarding minimization, because Q has class number 1, we can sort of do it one prime at a time. And one thinks a little bit about it. One figures out that it can always be done in this way. So maybe I'll explain this quickly. So the first thing is that so if you have a form of degree D and you act by a scalar matrix, then you scale all the variables by the same lambda. And because it's homogeneous, this means that you scale the whole thing by lambda to the power D. So if you then scale it by lambda to the negative D, then you don't change anything. So this means that we can always arrange for the matrix to have integral entries here. And then in general, if you have something like this, we can write M as a product of a unimodular matrix, a diagonal matrix, and another unimodular matrix. So that's not quite Hermite normal form, so I would like to have mentioned Hermite in this room, but it's slightly different. It's Smith normal form. And then since we just want to deal with invariants, well, with the p-adic valuation of the invariants, we don't want the determinant of this matrix M to involve other primes, so we can restrict to prime powers here along the diagonal. And we can write lambda as some power of p times something that's a p-adic unit. And so if we act on this by this on F, then we first have to act by T, which you see up there. Then we have to scale the variables, which you also see up there. And we can forget about U because U is unimodular, so it doesn't change the invariants. And then we scale by this power of P. And we can also forget about this p-adic unit because it also doesn't change the p-adic valuation of the invariants. And we want, if we do this over the integers, we want this to be plus or minus 1. That's how you get this statement. And then one has to figure out when this actually improves the invariance in the sense that the p-adic valuation goes down. And well, this is related to what I've written here. So scaling the variables has the same effect as scaling the polynomial with some factors, and the factors are such that you would have equality here. And if you want to gain more than you lose, you need to scale down more by more than you need to get the same thing. Which D is a degree of F. F is homogeneous of degree D, so D will always be the degree of F. Yeah, so that's what you need to actually gain something. Yeah, so there's a paper by Collard from about 20 years ago where he sort of sets up the general framework for this, and he calls this, I think, a weight vector. Now, if you fix such a weight vector, then it's not so hard to figure out that there are only finally many matrices T that you have to try, because there's a subgroup of GLN plus 1 over, well, yeah, I mean, there's a large group of matrices that doesn't change things here, and so you just have to look at cosets, and this subgroup has finite index. So in principle, once you fix the weight vector, it's a finite problem. But of course, the number of cosets grows like a power of p, so if p gets large, that's not good, and we want to have something more efficient later, but in principle, you can do it. But in order to really turn this into some kind of algorithm, we also need a bound on the weight vectors, because we need to know how many of them or which of them to try. And so here is a new result. So in the ternary case, when n is 2, then we can show that it's sufficient to look at weight vectors. So I mean, first of all, you can always have the entries ordered increasingly, because you can always permute them using some unimodular transformation. And then if they are all strictly positive, I mean, that means you just scale all the variables at least by p, and then you can divide again. So it's no loss of generality to have 1, 0 here. So we have 0, W1, W2. And then the claim is that we can actually bound all the entries by the degree d. And I mean, so the proof also gives a way of computing these things, and then, well, maybe I should first go a little bit further. So basically, the idea is that you can establish some kind of ordering between these weight vectors. It says that one weight vector, well, we say it dominates another one if whenever the other one can be used to minimize your form, then you can also use the first one. And so in the statement here is that the set of weight vectors of this form is so that every weight vector is dominated by one of these. And then once you know this, you can look at all of these and remove the ones that are dominated by some other weight vector in the set. And so you arrive at a minimal complete set of weight vectors for the given degree and n. And here's some examples. So when d is 2, so that's the case of conics, there are just these two weight vectors. And I mean, if you ever have tried to minimize a conic, which is more or less the same as finding a rational point on it, then you may have noticed that there are two cases in the process. One is easy, and for the other one, you actually need your p-adic point to know what to do. And this corresponds to these two weight vectors. For plane cubics, there are these 4. So I mean, this has been known for quite some time. There's an older paper by Kimona, Tom Fisher, and myself where we do this among other things. And if you look in this paper, I mean, if you forget the first 0 here, the leading 0, you'll find these 4 pairs of numbers somewhere. For plane quartics, there are just 3 of these weight vectors. And for quintics, there are a few more. And then, of course, well, we can compute these minimal sets of weight vectors for large degrees. And if you do this, you see that this bound d is close to optimal. So I think when d is congruent to 3 mod 6, then, and it's not very small, then the largest entry that you see is d minus 2. So we're not too far from the truth here. Anyway, I mean, as soon as you have a bound, you have an algorithm, at least in principle, and then the question is how to make this efficient. Any questions so far?
In the statement of the theorem, what does partially mean?
Partial means that you get something that's better than what you had before, but not necessarily the minimal one. I mean, the idea is that you keep doing this until you cannot do it further. Yep.
The vectors you skipped in this list are redundant?
The vectors that are not in this list are redundant in the sense of dominance. So if, say, if you look at 0, 1, 2 here, then you can show that if you can if you can sort of get a partial minimization using 0, 1, 2, you can also do it with 0, 1, 1. In this sense, they are redundant. Okay. Now, before I tell you how you do it for ternary forms, let me explain how to do it for binary forms, where it's a little bit simpler. So in this case, there's just one relevant weight vector. I told you the first entry we can assume to be 0. And it's easy to see that any weight vector dominates all its multiples, which means that we can restrict to coprime for vectors with coprime entries, and then there's not much that remains. So this is the only one. And then, well, assuming that we already have done the unimodular transformation, so we just work with the identity matrix here. If we can partially minimize this f using this weight vector, well, this means that using this weight vector means that we have to scale the second variable, which is y. So we plug in p times y for y. And then we want this to be divisible by sufficiently high power of p. And sufficiently high means in this case that twice e is larger than d, so e is larger, strictly larger than half the degree. And then you can work out what this means for the coefficients. If we scale y, we scale the coefficient aj by p to the j, so we add j to its valuation. And then the resulting thing has to be larger than half the degree, so well, we get this condition on the valuations. So this means that, well, when we are in the right half of this, excluding the middle if it's there, so when the degree is even, then this bound is negative, so it doesn't tell us anything. In the left half, we get some conditions, and in particular, all these coefficients have to be divisible by p, so valuation has to be strictly positive. And so if we reduce mod p, then we see a root of multiplicity larger than half the degree. So if you reduce this mod p and the first half of coefficients vanishes, then you get something that's divisible by the power of y with exponent larger than half the degree. But this now is a kind of geometric condition, which does not depend on the unimodular transformation that we have made. And so we can use this to write down an algorithm that minimizes binary forms. So we check this necessary condition. We factor f bar. And if we don't find a root or a linear factor of multiplicity larger than half the degree, we know that we cannot minimize it. So we just return it as the minimal one. Otherwise, there will be such a root of high multiplicity. And then we have to move it to 1, 0, which corresponds to the situation up here. So we find the unimodular matrix over the integers such that mod p, this multiple root, goes to 1, 0. And then we try whether we can do the scaling and gain something. So we transform f by t, we scale y by p. And then, so this means the minimum of the periodic valuations of the coefficients of this polynomial. So it's the largest power of p we can divide by without losing integrality. And then we check if this is large enough. So if e is larger than half the degree, then we get something better. And then we can try again to see if we can get something that's still better than this. And otherwise, we cannot get something better, and we return f. Yeah, so that's the idea. I mean, we have this necessary condition, which is of kind of geometric nature. If it's satisfied, then we know how to transform the polynomial to get things in a good position. Then we can do the scaling and check whether we gain more than we lose. And the same idea you will see later, only it gets a bit more complicated because there are more weight vectors. So that's the minimization, and then how to do reduction. This is explained in an old paper by John Cremona and myself, which is based, or yeah, which extends old work by Hermite, so I can mention Hermite here, and his student Julia, who is better known for his work in complex dynamics, but he started out as a kind of number theorist working on this. So he wrote his thesis on this reduction things. Okay, so I mean, we have a nice algorithm in the case of binary forms. Now, we want to do something similar for ternary forms. And so we want some kind of geometric conditions that are necessary for minimization that we can use in a similar way. So I mean, the point here is that we don't just run through all the possible matrices and cosets of some subgroup to see which ones can be used, but we use this kind of geometric condition to tell us precisely which transformation we have to make. So we want geometric conditions in the context of ternary forms. And I mean, the reason is what I just told you, that we don't want to run blindly through all the possibilities for t. We want something that tells us which t to take, which is efficient in the sense that it does not, so the complexity does not grow with p except in the sense that we have to do computations mod p. So it should be polynomial in log p, but not worse than that. So basically, it should only depend on the degree. So I mean, we always have these two weight vectors, 0, 0, 1 and 0, 1, 1. And we can do something similar to what I did with binary forms. Yeah, so we see what we get when we scale the last variable p or the last two variables by p, and then we want the resulting polynomial to be divisible by a sufficiently high power of p, and this gives us some conditions on the periodic valuations of the coordinates, of the coefficients, sorry. And so in particular, we know that a lot of these coefficients have to vanish mod p. And if we do this in these two cases, then we see that in this case, 0, 0, 1, the reduction, so f bar is the reduction of f mod p, splits off a linear factor of high multiplicity. I mean, how high depends on the degree. And if this other vector applies, then the curve given by f bar equals 0 has to have a point of high multiplicity. So there are lines and there are points. Before, if we were on P1, they are just points. So here we get two sorts of linear subspaces. And now they are, I mean, this is not the whole story because there are lots more weight vectors in general. But as it turns out, we can, in some sense, interpolate between these two situations. So, I mean, each weight vector, I told you that we can assume that these two entries are co-prime. So, weight vectors correspond to rational numbers between 0 and 1, basically, if we take the quotient of the middle one and the last one. And then this is 0, this is 1, so these are kind of the extremes. And so we can expect that for the weight vectors in between, we get something that's in between these conditions in some sense. Okay, since the conditions are sort of involve the geometry of this curve, I give it a name, that's x. X is the curve mod p defined by f. And then there's the following new result. So we assume that we actually can minimize, so f is not minimal at p. Then, which means there's one weight vector we can use to get something that's better than before. And then there are three cases, or three possibilities. So this is the case when we can use this one. So the curve contains a line with multiplicity larger than a third of the degree, which is sort of the analog of larger than half the degree of what we had before. Then there's an intermediate case. We still have a line of some multiplicity, but we have a little bit more. We also have a point on the line that has fairly high multiplicity, and I mean, which is larger than the multiplicity of the line, so it actually is a condition when the multiplicity of the line is at most d/3. And then the third case is in related to this one. So there's a point of high multiplicity larger than half the degree. And we can assume that this point is not on a line, because then if it were on a line, then they would be in case 2. And the reason why I want to assume that this point is not on a line is that this implies that this point is unique. So it's obvious for everybody. Yeah, so if you had 2 points, you could consider the line connecting the 2, and then this would intersect the curve with multiplicity larger than d, and so it would have to be contained in the curve. So the point would be on the line, which is excluded. And then, of course, there are at most d lines contained in the curve, because it has degree d, so you get a finite set of lines or points here, which is bounded by d, basically, in size. And then one can also show that, which is, I mean, not hard, that if we are in one of these cases, and then we apply the unimodular transformation that moves the line to a nice position, so to be the line at infinity, or the point to be this point, and apply this weight vector 0, 0, 1 or 0, 1, 1, depending on the case. Then, so by this, I mean, to make the transformation, we scale the variables, we divide by the largest power of p that we can divide by. We will not necessarily get something that's already better than what we started with, but in a precise sense, we get something that's closer to something that's better than what we started with. So, there's a kind of metric we can use here, and which corresponds, so the number of steps, so the distance, the decrease in distance to the minimal thing is given by the sum of the entries of the weight vectors here. Okay, yeah, I think every talk should have a proof, so here's a sketch of the proof that is the first part of the statement. The second part is not hard. Any questions? Okay, so I mean, the triangle represents the array of coefficients of your form of degree d. So here you have the coefficient of x to the d, y to the d, z to the d, and then you kind of interpolate. And maybe the other important information is this. So if we can minimize at p, this implies that we can remove factors of p, powers of p from all the invariants. So mod p, all the invariants are 0. And this says that the form is unstable when reduced mod p in a technical sense. And the condition for this instability in general is that, well, after you make a suitable coordinate change, you can draw one of these red lines through the midpoint of the triangle, and then for one choice of red line, all the coefficients in one of the half spaces, closed half spaces determined by it, have to vanish. And well, because of symmetry, you can restrict to, well, for the red line to be between horizontal and parallel to this side of the triangle. And then there are cases, and so we take the lower of the two half spaces here. So there are cases when there's just one of the vertices contained in this half space, and then you get a blue triangle like this that is, well, so its side length is, so if this is d here, then this is larger than half the degree, which corresponds to case 3 in the theorem. So you have, I mean, if all these coefficients vanish, then you have a point of high multiplicity, and the multiplicity corresponds to sort of how many of these vanish. This is kind of the case in the middle. But since we are looking for closed half spaces, this means that this coefficient vanishes and you already get a line. And in general, if you have two vertices in the half space, then half plane, then you get this situation. So you get all the coefficients in this green area that have to vanish, which means that you have a line of multiplicity, certain multiplicity, and then you also still get this blue triangle here, which means you have a point which is on the line of a certain multiplicity. And then you have to do some easy calculation to figure out that this is larger than d minus m over 2 when this is m. Okay, I hope now everybody is convinced. Yeah. So, yeah, from this we can deduce an algorithm for minimization at a given prime. So for this we need a bound on sort of the distance between our starting configuration and the one where we have something better. And this is, so this distance is given by the sum of the entries of the weight vector. So we need a bound on the sum of these entries here. So we can take, if we are lazy, we can just take 2d minus 1 from theorem before, and the fact that we can take w1, w2 to be coprime. Or we can just compute all the weight vectors, which doesn't take much time when the degree is not very large. And when the degree is very large, I mean, we have other problems anyway. And just take the maximum. So say for plane quartics, we had 0, 0, 1, 0, 1, 1, 0, 1, 3. So we would take m of 4 to be 4. And then basically the idea is the same as for binary forms. Yeah, we want to do some partial minimization as long as that's possible. But the new thing is that we now use the theorem from 2 slides previously to split this partial minimization into several intermediate steps using these simple weight vectors 0, 0, 1 and 0, 1, 1. So we use the theorem to find a list of pairs consisting of a unimodular matrix and a weight vector which is either 0, 0, 1 or 0, 1, 1. And as I told you, this list has length at most d, so the complexity is bounded in terms of the degree only. But of course, to compute t, we need to do some computations with integers mod p, so there's some dependence on p. And of course, we have to figure out whether there's a line contained, and so we have to factor the form over mod p and so on. So, but I mean, this can be done in polynomial time log p. Then once we have this, we try to see whether we get something. So for each of these pairs, we apply the unimodular transformation t to f. We scale the variables according to the weight vector. So we either scale z by p or y and z by p. We determine the minimal p-adic valuation of the coefficients, and then we divide by the largest power of p. That's possible. And then, yeah, so we may be lucky and have found something that's already better than the original f, and then we are happy and just return this. Or we can, so we will do this recursively. So if after some recursive calls we find that we have done this for too long because we exceed the bound for the steps that the maximum number of steps we have to go until we really find something better, then we sort of give up at this point. So in this tree of recursive calls, we just terminate this branch. And otherwise, we apply the same thing to f1. And okay, so if this for loop, if we get out of this for loop, then all the branches emanating from the recursive calls have been terminated without results. So in this case, we know that we cannot improve f. I should perhaps mention that there's another, so okay, maybe I first do this. So we have to keep track, of course, of the number of steps we have made so far, so the sum of the entries of all the weight vectors we have used to know when to stop here in step 2c. We also, of course, keep track of the transformations we have made in total, because we don't just want to return a minimal model for f, but we also want to say how to get it from the original one. I mean, we want the matrix and the scaling factor. And this also allows us to cut off some dead ends in the computation, because if we reach an accumulated transformation matrix with the property that all its entries are divisible by p, this means that we basically have scaled all the variables by p, which isn't something that brings us any further. So we have sort of made a kind of loop, and we can cut this off. So that's what we do in the algorithm implementation. Yeah, then so this tells us, well, either we cannot minimize, or we get something that's better, but of course it doesn't have to be the minimal one. So we repeat this until we get no further improvement. So I mean, yeah, if you really want to do it, it's a little bit more complicated because of the recursion and so on. But I guess anybody who is moderately adept at implementing things can go from here and do it. Questions regarding this? Yeah.
How does the running time depend on p?
Well, what you have to do is, so in the first step here, you have to essentially you have to factor f to figure out whether there are lines in the splits of linear factors over the finite field, which you can do, I guess, in polynomial time in log p, and then depending on the situation, you have to, well, you want this point on the line with a certain multiplicity, so you restrict the remaining part of your polynomial to the line. So you get a polynomial in binary form, polynomial in two variables, which you have to factor to see whether it has a root of sufficiently high. No, you just have to factor. And okay, if for the third case you have to find or to see whether there's a point of high multiplicity, but well, which is basically group basis computation over FP. Well, it's not so bad. I'm not sure whether one can say anything about the worst case complexity in the special case, but in practice it's not a problem. So the problem comes soon. Yeah, so I mean, this is basically polynomial time in log p, and so the list here has length d, the bound here is of order d, and so I mean, the worst case, if you get sort of the full branching, you get the complexity that's bad in d because it's something like d to the 2d times the power of log p, but in practice that's not what's happening. So in practice this is quite fast, and I will show you. Okay, so I mean, this is great. Yeah, we can do this minimization at p. But of course, if you want to get a minimal model for a given polynomial, there's a catch. We have to do something more. What's the catch here? Sorry? Yeah, so I mean, we can do it for any given p, but we have to know for which p we have to do this because there are infinitely many primes. So we cannot do it for all of them. And so the part of the problem is to figure out which primes to try. And this is, of course, a global thing. And so global parts of these computations tend to be hard. And it's also, in practice, the part that usually takes the longest. Yeah, so what can we do? We have these necessary conditions. Yeah, that, I mean, you have to have a line of certain multiplicity and a point on it of certain higher multiplicity mod p, these things from the theorem. And these conditions, well, can be formulated as a system of polynomial equations and the coefficients of the polynomial. Well, not the coefficients in sort of the how you parameterize the line and the point on it. So you get So in a generic case, I think you get, what do you get? You get 3 variables. So you get a system of polynomial equations in 3 variables over the integers. And then in principle, you can just write this down and do a Grignard basis computation over the integers. And then all the primes that are such that this necessary condition is satisfied, mod p, will have the property that they divide the integer that's in your Grignard basis, assuming there is an integer in your Grignard basis. Otherwise, you don't get any restriction on the p's. Yeah, so there, I mean, you split this into various cases depending on how the line, the point lie with respect to the standard affine patch of your projective plane. But I mean, that's one thing one can do. But in Grignard basis computation, global ones tend to be slow, or at least they can be fairly slow. So another possibility is to say, well, the condition, I mean, precise condition, well, okay, so necessary condition is that the form mod p is unstable, which means that all the invariants are divisible by p. So if you could just compute all the invariants, and then take the GCD, and this would, I mean, factor this, it would give us the potentially bad primes. But of course, we don't know what all the invariants are in general. I mean, I think we know them for up to plane quartics or so. But I mean, it's not so hard to at least compute a few of them, say 2 of them. Take the GCD, and so this gives an upper bound for the primes. And then we use this GCD as an additional generator for the ideals on which we do the Grignard basis computation. And this basically has the effect that we do the Grignard basis computation modulo this GCD, and so we avoid this intermediate coefficient growth. And so things go a little bit faster, but I mean, so claim that this runs in reasonable time. Of course, it depends on what you think is reasonable, and of course, it depends on the size of the coefficients and the degree. But it's still the time, the part of the procedure that usually takes the largest part of the time. Okay, so here's the promised slide on reduction. So I hope it's okay if I try to pitch a paper of mine that's, I think, could get more attention. But so that deals with a similar problem.
For the previous problem, can you use a lazy factorization thing where you pretend that the things you're not a factor?
Probably. So Bjorn asked whether it's possible to use something like lazy factorization to avoid factorization as far as possible in the previous problem. So here.
Do you have to solve polynomial equations?
Well, we have to solve polynomial equations basically, and so I mean you can do a little. You can try to use coprime factorization to some extent to push off factorization until the end, but at some point you have to factor. But I mean, say if you have a smooth plane curve of not very small degree, then you will only find a few visibly small primes usually, so that's not so bad.
Maybe you can prove that this problem is as hard as factorization.
Well, I think actually global minimization of ternary forms is as hard as factorization, at least. I think it's random polynomial time equivalent or something, because you can look at conics, and for conics it's basically, I mean, so minimization of conics is the same as finding rational points on them. Yeah, so this paper is sort of a generalization of the other paper I mentioned by John Cremona and myself. It deals with reducing a bunch of points in Pn. So a bunch of points is a technical term. It means this. And so we want to to find a unimodular transformation that moves these points so that they're kind of spread out nicely with respect to the coordinate system chosen. And then we can use this to do reduction of ternary forms by associating to the ternary form some cluster, some bunch of points in a covariant way, so covariant with respect to the action of PGL, so the automorphism group of P2 in this case. So one thing that comes to mind is we can use the inflection points. So we take the curve, we take its Hessian, and the intersection of the two. This gives a bunch of points. Actually, inflection points is maybe not such a good idea because the number goes quadratically in D, and we can take other covariants than the Hessian to get something that goes only linearly or so. But I mean that's basically the idea. And then we apply this thing which has been implemented in Magma since some time. And another thing, so in practice, it's actually quite efficient to just do the obvious thing, which is you try some small transformations, like replacing x by x plus y and things like that. And then you see if you get something smaller. If yes, then you try again, and you keep trying this until you get stuck. And in most cases, this actually gets you down to something pretty small. But sometimes it does get stuck, and then you need to use the more sophisticated thing to get it small. Yeah, and then also kind of practical thing is it's also usually a good idea to do some kind of reduction in between these minimizations for different primes, because if you minimize at a large prime, then this tends to blow up the coefficients. And so if you then make them smaller before you take the next prime, that simplifies the computation.
What does the word reduction stand?
Well, you reduce the size of the coefficients, I suppose, in some sense. But I mean, so I mean, both terms, minimization, reduction, roughly mean something similar. But I mean, you want to distinguish between these two things. So, okay, so here's some examples. So first are two plane quartics from a paper. There's 3 authors, 2 of which are here. So at the time when the paper was written, some effort was taken to get nice models of these, but so the theory was not yet there. And turns out, I mean, there are more than these 2, but the others are already minimal. Turns out that these 2 are not minimal at 2, and we can minimize them and get something that's minimal, but it's maybe debatable whether they are better equations than the ones we had before. So in the first case, we get more terms. In the second case, we get actually larger coefficient. But from an arithmetic point of view, they are better because they're minimal at 2. I should say that so the case of plane quartics was already implemented by Stephan Elsen Hans. So he worked out how to do it in this case and implemented it. And so what's new is that we can do it for all plane curves of any degree. So here's another example. Anybody knows this curve? Well, it's a preprint right now, and I'm not one of the authors. Okay, so one of the authors is actually here, so he should recognize it. So that's a model of a certain modular curve. And so maybe one thing to point out here is that this is not a smooth model. It's a model of a genus 6 curve, and you have a model of degree 6, so it cannot be smooth because then we have genus 10, so it has to have 4 singularities. And yeah, so I mean, you can just run it on the algorithm on this, and we get this one. So it turns out that this is not minimal at 2. And we get sort of this model which has quite a bit smaller coefficients. I mean, there's one aspect in which this model is maybe worse than this one, and this is that this model is is even in Z. So, so I mean, you see that it has an involution that you don't see immediately here. Of course, the involution is still there, but it has a more complicated form. Okay, and now I'd like to actually show it. I mean, this is for this, I mean, what you see for this example. And I should point out that this matrix here is the transpose of the one that I used in the slides. But I can sort of show you. So this just attaches the code. So it tells you what's, so you, I mean, sets these verbose flags so that we see what's going on. This defines the polynomial ring. And then this is this example. So you also know now who the authors are. And so, I mean, this is the function that does all of this. And so it's, I mean, this is pretty fast, but the coefficients are fairly small. So maybe I go up a little bit. So the first thing here says unstable primes must divide this number. This is the GCD of these two invariants that we compute. And then it looks through the various possibilities in the theorem using this information as a starter. So it figures out the condition to have a highly singular point, so case 3 in the theorem. And then, so I mean, you see 7, 16 is, this means potentially primes 2 and 7. And then it works out the condition that one can split off a line, and then using this, so the more precise conditions on lines and points. And so this gives us, in the end, that you only have to look at 2 and 7. Then it does this ad hoc reduction at the beginning and in between. So now it looks at 2. And so you see here how this recursion works. So gamma is a measure for how much better or worse the polynomial gets. If gamma goes up, it gets worse. If gamma goes down, it gets better. And if gamma gets negative, we have found something that's better than originally. So you see it first goes up to 3 and 6. And then you see the cycle detector. This is when the transformation matrix becomes divisible by P. And so there's a kind of whole subtree that doesn't lead to anything. And then sort of the second try, one level down, gives something that's better than before. So gamma is negative. And then tries again and doesn't find anything. So there's just this one minimization step. And then does the same at 7, so where it doesn't take very long to figure out that you cannot minimize. Then, I mean, there's this ad hoc reduction that basically already gives the final result, but it still tries this cluster reduction, but doesn't get anything better. Okay, and now here's a random example. I just defined two functions that generate a random polynomial of fixed degree and size of coefficients in the random matrix with entries of a certain size. So I create a polynomial of degree 8 with small coefficients and take a matrix, 3 by 3 matrix of integers of 10-digit size and hit it with this. I don't show you F1. I mean, I could, but it would just fill the screen pretty quickly. And then you see what happens. So, of course, this is a random experiment, and I tried it for many examples. And so the median running time was something like 40 seconds, but in some cases it can take a few minutes, so we'll have to see. Yeah, so I mean, the first thing, again, this is the GCD of the invariants. And then this is for the singular point. Then this usually takes a fairly long part of the time to figure out the condition for a line to split off. And also sometimes the next one takes some time, but I mean, not much longer than this. And then the other ones are usually a bit faster. And then, okay, so this took close to a minute, but in the end we are basically back to where we started. Okay, so yeah, I guess I should leave the last minute for questions. Thanks.
Thank you. Are there questions or comments?
So if I understand correctly, when we saw the live trial, like any time that you're not minimal, as you say, there's going to be powers of p in those invariants, and I suppose a number of powers of p according to the weight of the invariant or something like that. But the fact that that number that the non-minimal primes must divide is like much bigger than the amount you actually reduce. Like in that first example, I think you only used 2. So does that mean there's lots of cases where, on grounds of what divides the invariants, it looks like it might not be minimal, but it actually is? Is that what happens?
Well, what we do here is we just compute 2 invariants, and not all of them.
Oh, I see.
So, I mean, it's good to have more than one, because in one invariant you get lots of random primes usually. So if you take 2 and take the GCD, you should get something that's not too far away from what you really want. But I mean, of course, ideally you would have to take all the invariants, or generating set of all the invariants and take the GCD. So this is why this first bound looks relatively large. I mean, of course, in this case, let me see.
So I guess I'm asking, if you did take all the invariants, do you think that would reliably give you the list of the primes that are non-minimal and no others, or would that?
Well, so I mean, the vanishing of all invariants tells you that the form is unstable mod p, which is a necessary condition, but not a sufficient condition.
Yeah, that's what I'm
because, I mean, what you also need, at least, is that each invariant is divisible by a power of p that corresponds to its weight. And of course, you don't see this when you reduce mod p. You just see whether p divides it or not. Yeah? So if p divides to the first power some invariant, but the invariant scales by squares, if squares of the determinant, then of course it's also minimal. So if one could compute all the invariants, of course one could then check each of these primes, so dividing the GCD, whether it divides each of the invariants to the right power. But since we cannot do this, we have to use something else that works. So I mean, in this case, you see these are the primes. I mean, there are some very large primes. I mean, it's basically just the primes dividing the determinant of this random matrix. And I mean, in examples like this, except maybe for very small primes that always divide these invariants, because I didn't try to figure out precisely what's the kind of largest integer that divides them uniformly. But except for them, of course, in these examples, they all will give you something. And so I don't think you lose too much this way. And anyway, I mean, it's also a compromise. I mean, the question is how much work you want to put into computing invariants and how much work in the other part.
More questions? If not, let's thank the speaker again.